Am I audible to you? Am I audible? Crazy. You are not aware of this responding also. Sasat, am I not audible? Am I audible or not? Sasat. So crazy these people. Can't imagine it. After just joining, left. Sasat. Sasat, are you listening? Sasat, are you listening?
Yes, sir. Now you are audible, sir. Sir, I wrote in the chat, sir, not audible. You can see because you were not audible that time.
Now it is audible.
Yes, sir. Yes, sir. Now it's coming, sir.
And slide is visible, slide.
Yes, sir.
So last times discussing the power budget analysis and right time budget analysis. Are you present in the last class, Sasat? Are you present?
No, sir.
You are absent last class.
Yes, sir.
Okay. So last times we have discussed these two link analysis methods. One is power budget analysis, and that is the right time budget analysis. In the power budget analysis, we have seen generally we consider the linked loss models. Linked loss models, right? I told you we are discussing in this chapter discussing the transmission link analysis. Means once you choose the components, sources, detectors, fibers, connectors, splices, etc. Next, you have to see whether those components can meet the system requirement. Means system requirements, I told you three key requirements are there: transmission distance, data rate, and data rate or bandwidth, and the bit error rate if it is digital systems. Right. So that is the key requirements. So after choosing the components, you have to check whether the components can meet the system requirement or not. You need some digital distance, you need some digital data rate, and you need to satisfy some bit error rate. So to check all those things, I mean to determine the performance evaluations, actually you have to consider the two methods. One is power budget analysis and the right time budget analysis. In the power budget analysis, generally one considers the link loss models. Last time I discussed it. I'm just giving the highlights. In the link loss models, what are the losses involved that you have to see? It considers the total losses in the systems. Say this is the transmitter side source. Next, there will be a connector. One connector is here and another connector is here in the detector side. These are the two connectors. These two connectors must be there. So you see, apart there can be connectors in the link also. This is but that can be optional. Connectors also there will be splices. I told you connectors are the permanent connections, because connectors are used for permanent, sorry, connectors are used for temporary connections. I mean, you can connect or discount it, not whole device. But splices, they're the permanent joints. When you join two fibers together permanently, that times these um, splices are used. They are the splices. These are also optional. Right. So there'll be connectors loss. So once you use the component, some loss will be there. So there is a connector loss. There can be splice loss. Also, the fiber itself can produce loss. The fiber attenuation that we have studied, that is alpha F. So in the link loss models, generally one considers a total loss. Total loss, that is actually first actually he determines the power difference between the transmitter and the receiver sensitivity. Keep in mind receiver sensitivity, that is the minimum power that can be detected. So that power is now allocated to these losses, just now what I mentioned, right? So PS minus PR, this power difference. And what are the different losses? This is LC connector loss. Now the question is, what is 2 plus N? 2, I told you, one at the connector side, one at the source side, another a detector side. So that's why 2 must be there, twice LC will be there, but there can be some optionals. Optional LC also will be there. If there is no, in the problem, if you see there is no optional, there is no extra connectors, so twice LC you must write it. So this is optional actually, optional, right? Uh, Next, N primes LSP. So similarly, LSP will be the connector splice loss, and there can be N prime numbers. I mean, certain number of splices will be there. So that depends the number, the value of N primes. Alpha F, that is the loss dB per kilometer. So if the total link length is L, then alpha F times L, that is actually the fiber loss or the cable loss. Plus some system margin should be considered, that is 6 dB. That is because of aging, because of temperature variation, etc. Some additional loss should be considered, that is the system margin. That is generally 6 to 8 dB, 6 dB. Fairly you can assume 6 dB. So, so from these expressions, you can find out if all the parameters known to you, then you can find out what should be the, with the chosen devices components, what will be the maximum transmission distance L. Generally that is asked. For examples, it is given here as a source, it is minus 13 dBms. Actually 50 microwatt, if you just convert it into, that will be minus 13 dBms. Right, dBm equal to this one, P by 1 milliwatt, log P by 1 milliwatt. PR, the receiver sensitivity minus 42 dBm. So first of all, if microwatt or milliwatt is given, then you have to convert it into dBms. So PS minus PR, you see it. So PS, it is minus 13 dBms, minus 40, minus 13 dBm, it is more power, minus 42 is less power. More negative means less power. So minus 13 minus plus 42, that will provide the 29 dB. Right, below dBm means that is actually 29 dB below 1 milliwatt. So that is 29 dB, and that will be equal to this one. If you know the connector loss, if you know the splice loss, say it is 0.5, it is 1 dB per, that depending on the number of splice, number of connectors, you can find out plus 6, and from there you can find out L. So that is the things at the end. Also, graphically also you can determine this distance. And just now you have seen this in the graph, you see that is the power levels and that is the distance. Now, say source, if it emits minus 13 dBms, so that is actually these ones, minus 13 dBms. Here it is in the power levels, right? There is a power launched into the fiber. But when it is coupled into the fiber, so connector loss will be there. So this is connector loss. Connector loss, it is, say for example, earlier it is what I have considered. That in the examples, connector loss 1 dB per kilometer, 1 dB per connectors. You can see it here, these ones. So minus 13 dBms, so it will be 1 dB less here, right? 1 dB loss will be there. And if the receiver sensitivity, say minus 40 dBms, minus 40 dBms in the examples, you can see it now, minus 42. Minus 42 dBms, but say connector loss will be there 1 dB, right? So you can see it here. So 40 estimate why it is 42 dBms, right? Minus 42 dBm and minus 42, and this is 1 minus 6. Right. This is the connector loss. So connector loss will be 1 dB. 7. So it will be 35. Right. So here it will be 35. Here, if you connect this connector loss plus 6 dB margins, so it is 7. 7, if you just consider it 7 dB, that means it will be here, it will be somewhere, it is 35 minus 35 dBms, right? So, and so if this line, if you consider here also just 1 dB per loss in this case, and this line, if you from this line, this is 6 dB margins. So if you join, if you just extend this line, that is the cable loss. This is the cable loss. Of course, cable loss plus price loss also will be there here, right? So that line, if you just consider, right? So that will be, say, intersects at this point, right? At this point, that will be the distance with the chosen parameters. So graphically also you can determine. I mean, it is very simple. This is the connector loss. This is connector loss. This is 6 dB margins, and so this if you extend this line, somewhere it will intersect at this line, right? So where does it intersect? That will give you the distance, maximum distance that is possible with the chosen components. And this actually slope of this line, it is alpha f, that is 3 dB per kilometer, say 3 point, if you consider 3.5 dB per kilometer in the problems, you can see it here. Alpha f we have considered, it is alpha, you see it here, 3.5 dB per kilometers. Plus some, this loss also will be there. This loss means splice loss will be there. So that lines, right? The slope of the line. So this line, where does it intersect? If here, that will give you the distance. And this is the graphical. Graphically, you can determine the distance without expressions. Anyway, so this is the power budget analysis. In the power budget analysis, you can determine what should be the maximum distance. Right. If it does not meet the distance, that means you have to change the components, right? Or maybe you have to use the repeaters. So after completion of this power budget analysis, next the designer will do the rise time budget analysis, right? Rise time budget analysis, and that is essential for digital fiber optic links. Digital fiber optic links. What is the principle of this rise time budget analysis? What are the things are considered here? In the rise time budget analysis, that is generally used for digital fiber optic link, what the designer first considers the total system rise times. Total system rise times. Total system rise time T systems. What is that? Total system rise times. It is the you see. Square root sum square the rise times of each contributors. Root sum square rise times of each contributor to the pulse times pulse rise time declarations. Actually, this is related to rise time declarations. Pulse rise time declarations. So that is the sum of, say, suppose n contributors are there, then it will be 1 to n ti square. That means root sum square maybe a square of the each contributors. What are the different contributors? You see, I mean TI. Say what are the different TIs? It can be transmitter rush times, that is TTX, transmitter rush time 1. Another one is the fiber modal rise times, that is T modals. Third one, material dispersion rise times, that is T materials. And fourth one, the receiver rise times, that is TRX. So there are 4 contributors, in fact, in these digital fiber optic links: transmitter rise times, fiber modal dispersion rise times, material dispersion rise times, and receiver rise times. Right. That means generally most of the cases n equal to 4, 1 to 4. Right. And while considering these system rush times, one thing should be considered to determine the system performance. The total system rush time should not exceed the 70% of the NRZ bit period. If it is NRZ systems, generally you have considered these digital systems, so either it will be NRZ or RZ. These are actually different versions. I mean, Manchester coding also, etc. Those things are there. So from these all similar things you can determine. So if it is NRZ data streams, then total system rush time should not exceed the 70% of the NRZ bit period. And if it is RZ, I mean, here there is no mid-bit transitions, but here mid-bit transitions will be there, RZ, Manchester, etc. So in that case, total system rush time should not exceed the 35% of the NRZ bit period. That you keep in mind. These things should be kept in your mind. Otherwise, in the problems, maybe you'll be able to calculate system rush times, but questions will be asked where whether the components meet the system requirement or not. Then you have to check it whether after calculating these system rush times, you have to verify these ones. I'll show you some examples. And NRZ bit period, actually, if you know the data rate, then inverse of the data rate actually bit period. Suppose 20 Mbps. If it is 20 Mbps, the data rate, NRZ data, then 1 by 20 into 10 over 6, that will give the bit period, right? And inverse of data rate. And multiplied by 70%, 0.7, it will give you this one, 70% of the this, right? Bit period. That should not I mean, system rush test will not exceed that. If it exceeds, then you have to change the components. Right? I mean, you can verify it whether the components can meet the system requirement or not. So now let us see what are the different expressions for these contributors. Generally, out of these 4 transmitter rush times, it depends upon the LED source, LHS source, etc. And it is generally known to the designer, right? Transmitter rush time generally known to the designers. Once you procure the light source from different vendors, they will provide these transmitter rush times. So transmitter rush time directly you can have it, right? Receiver rush times, you see, receiver time generally depends on the receiver bandwidth. If receiver bandwidth is BRX, right? Then the receiver rush times generally it determines from the step response. I mean, step response of photodetector response. This can be determined from the photodetector response and also the 3 dB bandwidth of the receiver rush times. In fact, we have seen this. If you consider the receiver circuit, we have seen the receiver circuit can be modeled as a low pass filter, right? and the step response of that receiver, right, can be expressed like these things. GT, step response GT, that is 1 minus exponential minus 2 pi BRXT UT. UT the unit step functions, that is equal to 1 when t greater than 0, and it is 0 pt less than 0. So unit step functions, right? So that is the photodirector response, can be modeled like these ones. And the rise times corresponds to, rise times, if you have a step response, step input, you see it here. Rise times, it is 10% to 90%. It is the time difference between this 90% to 10%. That is the rise times, receiver rise times. So if the response is these ones, once you put GT equal to 0.1, and other case GT to 0.9. So if you just consider these two, and if you find this receiver rise times, then it will be TRX after substituting these things, two cases. Once you put 0.1, another case 0.9, then you can find out TRX, the time difference between these two. That will be actually 350 by BRX. Directly can be this TRX, it is in nanosecond, and BRX in megahertz. It is not too difficult. You can find out this one. Now, what is BRX? It's bandwidth that we have seen. It depends on the total resistance and total capacitance 1 by 2 pi RTCT. So that is the receiver rise times, 350 by BRX. And so directly, if you know the BRX, then you can find out what is the receiver rise times, right? That in nanosecond. Keep in mind, it is in megahertz, it is in nanosecond. If you use these relations, then it must be nanosecond, it must be in megahertz. That is the receiver rise times. So you can now, the transmitter rise time is known to the designer. Receiver rise times can be calculated if you know the receiver bandwidth, right? Next, the metal dispersion rise times. Metal dispersion rise times, we have seen these metal dispersion expressions, that is d materials, d2 n upon d lambda 2, that we have seen it, times sigma lambda means it is the bandwidth times L. This expression we have seen earlier in the metal dispersions, right, as a pulse burning. So, right, that is a standard expressions for metal dispersions. Now here, of course, you can neglect this metal dispersion if wavelength is around longer wavelength side. I mean, 0.9 and above. So if it is 1.55 microns, then you can consider T metal can be 0, say AR. But if it is short wavelength regions, say 0.7 to say 0.9, if it is operating wavelength these ones, then of course you have to consider this factor D materials, that will be 0.07 nanosecond per nanometer per kilometer times the spectral width of the source times the link length. So you have to calculate, right? If it is in the shorter wavelength side, but longer wavelength side, this factor can be considered, whole factor can be considered as 0, right? Because you have seen it. If you see the metal dispersions, then it is like these things. So in the longer wavelength, say 1.27, somewhere it is 0 for silica. 1.55 also it is very near to 0. So you can neglect it. But if it is the shorter wavelength side, then you have to consider 0.07 nanosecond per nanometer per kilometer. So that is the metal dispersion rise times. So we have seen 3 contributors: transmitter rise times, receiver rise times, and metal dispersion rise times. Now the fourth one, which one is the fourth one? You can see it here. Fourth one is fiber modal dispersion rise times. You see that ones. Fiber modal dispersion rise times, to calculate it is very complicated things, because you see in a link, in a biotic systems, biotic link, Generally, it's not a single fiber. There can be several fibers will be there in between, and for each fiber, the modal distribution, though it is single, if it is a single mode, but still there can be parameter variation like alpha variations will be referred index profile, little bit variation will be there. But for particular for multi-mode, modal distribution will be different, right? So, so it's a very complex phenomena to determine these fiber modal dispersion lifetimes. Anyway, if you generally for this purpose, generally empirical relations are used. Empirical relations means based on field experience, practical field experience. Some empirical relations are used, and in that relations, generally, a modal dispersion lifetimes it is expressed in terms of fiber bandwidth. Fiber bandwidth. So if you know the fiber bandwidth, then you can find out the fiber modal dispersion lifetimes. Fiber modal lifetimes. Now the fiber bandwidth generally just I mentioned different. Actually, fiber modal dispersion lifetimes it depends on this fiber bandwidth. Fiber bandwidth it's very difficult to find out because of the different sections of different fibers. So, but some empirical relations are there, right? One of such relation is you can see it here for fiber bandwidth. Fiber bandwidth, it is, you see it here, BML, bandwidth over a distance L, that is B0 divided by L to the power Q. What is B0? B0 is a bandwidth for 1 kilometer length, right? And L to the power Q, L, the actual distance that will be that you have to consider, a link length. And I mean, this is BML over a length L bandwidth, that is the length L, and L to the power Q. Q actually it is known as the mode mixing factor. Generally, it is 0.5. If it is 0.5, then modal distribution, equilibrium steady state modal distribution would be there, right? Generally, it values its value it varies between 0.5 to 1. 1 means there is no mode mixing, right? That is the ideal case. But generally, some mode mixing, higher lower mode to higher mode, higher mode to lower mode, some mode mixing will always take place. So fairly, you can assume if it is not Q value is not given, you can assume the value of 0.7. 0.7 you can consider. So L to the power 0.7. That is one of such bandwidth expressions. But there are other expressions also there. Like say 1 by one more expressions you can see it here, 1 by B to the power A. So BM or fiber bandwidth, that is actually summation of 1 to n, n equal to 1 to n, right? That is 1 by Bn all to the power 1 by Q all to the power Q. There is another expressions for fiber bandwidth. Where Bn, it is the bandwidth of nth fiber. There's several fibers are connected together. Then that is the Bn is the bandwidth of that particular nth fiber. So in this way, you can determine the fiber bandwidth. Generally, widely used expression is B0 L to the power Q. So we'll consider these ones, right? Next, after so that is not the sufficient. You have to determine the modal dispersion lifetimes if you know the full width at half maximum. And let us see how it can be calculated. These ones from this fiber bandwidth. Then only if you know the full width at half maximum, then you can find out the fiber modal dispersion lifetimes. So for that, suppose you have launched power within a fiber, and output of the fiber, we assume it is Gaussian. It is Gaussian response. If Gaussian distribution is here at the output at the output end, then you see the response can be expressed as GT 1 by root over 2 pi sigma e to the power minus t square by 2 sigma square. That is the Gaussian expressions, Gaussian distributions, right? So this is the Gaussian temporal response we are assuming at the output end of the fiber. Now, if you take the Fourier transform of this one, then it will be g omega, integral of 0 to infinity, you can gt e to the power I 2 pi minus 2 pi I 2 pi ft dt. So if you consider that once, then after performing that the Fourier expressions, Fourier transforms, just a minute. Assuming it. I mean here, Fourier transforms, that is actually say g omega directly here. Actually, you have to perform the integrations. That is g omega. Actually, it is say minus infinity to plus infinity, or you can say 0 to infinity minus infinity. By definitions, it is gt e to the power minus I 2 pi ft dt. And GF, right, dt. So that is the definition for transforms. So once you get this GT, I mean F instead of F, you can write G omega. So it will be omega also here. So 2 pi F, that is the omega, 2 pi omega t, right? So after taking the Fourier transforms, you'll get g omega. So if you substitute the value of gt here, then you can find out 1 by root 2 pi e to the power minus omega square sigma square by 2. Sigma is the RMS pulse width, right? That is the Fourier transforms. Now here one such term you have to consider, that is t half. And that is t. What is t half? Is the time required for the pulse. So we have learned some pulse. Is the time required for the pulse to reach its half maximum value. To reach its half maximum value, t half. Then you see g of t half. Then we can write it. You see half maximum value. That means 0.5 of g0. If you put g0, that is a maximum value, right? And gt of half, that will be the 0.5 of g0. So once you get this g0, put t equal to 0 here, next year put t equal to half. So that times t can be replaced by t half. So from and gt that times gt of half is 0.5 of g0. So if you just solve these expressions, then you can find out t half, that will be twice log of 2 whole to the power half times sigma. This will be, you will get this one. I think it is quite clear how you'll get it. You put g t equal to 0, g0. So it will be, this factor will be there because this will be 1 by t square. So t equal to 0. That means it will 0, 1 will be there, right? So this will be there, and again t half, that will be t half. So this and if you substitute this one, consider these conditions, then from this, if you solve for t half, then you can have it twice log of 2 half of sigma, right? So that is t half. What is t half? Just now mentioned, it is the time required for the pulse to reach its half maximum value, right? Now I told you we have to determine the TFWHM, full width at half maximum for Gaussian response. So that will be twice of t half. TFWHM, full width at half maximum. You can see this one, full width at half maximum. So just now I have seen this half, it is t half. So twice of t half will be there. So that is the full width at half maximums, right? 2 of t half, that is twice sigma, twice ln2 whole to the power half. If you find out the t half, just that we have seen it. Now, so it is now we are getting this full width at half maximum or Gaussian response. Now, what is fiber? What is the 3 dB optical bandwidth? 3 dB optical bandwidth, it is actually f3 dB that corresponds to half power point. That is a conventional definition of bandwidth, corresponds to half power point. So you have seen this for transform G omega. So, and maximum value will be omega equal to omega 0, right? And half power point will be 0.5 of G0, G of omega 0. So if you have to consider this G omega 0, you see it here. G of omega 0. That means actually that will be omega equal to 0, right? So here you can see it here. G omega already have determined here G omega. So once you put omega equal to 0, and next and omega equal to omega equal to 3 dB. So from that also you can find out omega 3 dB and G omega 3 dB equal to 0.5 of G0, right? Like these ones. So you'll get it. Actually omega, this is 0, not this is 0, G0, right? So so you'll get it. If you solve it, then f3 dB, you can find out optical 3 dB optical bandwidth, that is 3 dB, and you'll get some factor. That factor can be, you'll get the factor like this one. So those factors are replaced by TFW HMs. You see, ultimately you'll get it 0.44 by TFW HMs, right? So you are now getting a 3 dB bandwidth, 3 dB optical bandwidth of the fiber link, right, from the fiber bandwidth. Now you can correlate with the fiber bandwidth, right? So you see modal dispersion as times, the modal, that is our point, modal dispersion as times. That is actually now this TFW HMs, that is actually the modal dispersion as times, TFW HMs, right? Resulting from the modal dispersions. So so this can be, it is 0.44 by B3 dB. And B3 dB, it is now replaced by BMs. That is the fiber bandwidth, right? So fiber bandwidth, that is, what is that? That is B0 L to the power cube, that we have seen it. Empirical relations are there. You can see it here. We have considered here, you see B0 L to the power cube. So you see it here. Just putting the value of BM equal to B0 L to the power cube, you'll get it 0.44 L to the power cube by B0, right? So if you know the link length and if you know the Q factor, this Q factor, Q is a mode mixing factor, then, and if you know the B0 per bandwidth of 1 kilometer length, then you can find out the modal dispersion as times, right? So you can calculate these modal dispersion as times. And Q value is generally, it is, if it is not given, then you can assume 0.7, or you can consider 1 also. So if no time is here, then for simplicity, you can consider assuming no mode mixing, Q will be equal to 1. Then quickly find out modal dispersion as time. So everything's are known to you now. You have seen this. Yes, this one. So your T system square, we have seen this root sum square as time of each contributors. So if you consider, take the square of system as times, so T system square, that will be T TX squares, T RSS squares, T modal square, and T material square. So what are the expressions? TTX generally is given to you. It is generally vendors are providing this one. TRX, if you know the receiver bandwidth, then you can find 350 by BRX, that we have seen it. T modal dispersion and last we have seen it is 0.44 by BML, at 0.4 by L to the power B0. Now, if you express it in terms of nanosecond, T modal in nanosecond and B0 in megahertz, then 4.44 will be 440. So directly you can use the relations, provided that it is in nanosecond and it is in megahertz. So 440 L to the power cube by B0 plus d material square sigma lambda square L square. So if you know all those things, then you can find out the system lifetimes. So one example is this, you see it here, suppose TTX, receiver transmitter rise time is 50 nanosecond. Say spectral with delta lambda or sigma lambda, delta lambda or sigma lambda is a 40 nanometers. L distance, say 6 kilometers, you want to cover it. Receiver bandwidth, say 25 megahertz. Fiber bandwidth B0, it is a 400 megahertz kilometer. Generally, it is expressed megahertz kilometer, right? B0. And D materials, suppose if your operating wavelength, it is a 0.885 microns or 850 nanometers. Then if it is mentioned, then you have to consider this 0.07 material dispersion factor. If it is a 1.55, then you can neglect these expressions. The expression can be considered as 0. Very little contribution will be there. Substituting all these things, TTX square, these things, if you calculate, we know all the values, if you put it, it will calculate, it is system lifetime will be 30 nanosecond. Square root of this one will be 30. And take the root, calculating this square, next take the root, you'll get 30 nanosecond T systems. Now, this is not the end of these problems. You have to check it whether it meets the system performance or not, system requirement or not. So for that, say generally the problem will be mentioned, energy data streams of say 20 Mbps energy data stream is used. Then you have to find out, say 20 Mbps energy data is there. Then you have to find out what is the allowable time, system lifetimes. So that is 70% of the energy bit period. So 1 upon 20 10 to the power 6 inverse of that is data rate, that is the bit period, times 70% 0.7, that will give you the 35 nanosecond, 70%. And just now you have calculated system lifetime 30 nanosecond. So it is below this one. That means your answer will be yes. Yes, these the components the system requirement. That will be the answer. So after verifying all those things, so that is these ones. That is the final form of this the Einstein link analysis. If you have any questions, you can ask. It's the most important things, the two budget analysis. One is the power budget analysis, and the another one is the Einstein budget analysis. बोलो किसी का कोई क्वेश्चन है तो पूछो. सो नहीं रहा है तो पूछो, सो रहा है तो बस ठीक है. किसी का कोई क्वेश्चन है तो पूछो, और नहीं तो बोलो नहीं. देखा जाएगा क्विज में, एंसर में. किसी का कोई क्वेश्चन है? यस और नो तो बोलो.
नो सर.
हाँ बोलो बोलो.
नो सर.
हाँ ओके. एक तो कम से कम रेस्पॉन्ड क्या, सो नहीं रहा है. बाकी लोग तो सो रहा है, सोने दो. ठीक है. कोई क्वेश्चन नहीं है ना, तो क्विज लेकिन फ्राइडे होगा. फ्राइडे टाइमिंग हम लोग नेक्स्ट क्लास में डिसाइड करेंगे कब होगा. शशांक
सब फ्राइडे पहले ही क्विज है.
फ्राइडे तो हम तो 15 दिन पहले ही बता दिए थे हर्षवर्धन को जो फ्राइडे क्विज होगा. टाइमिंग अपना सेट कर लेना कब होगा. वो कल हम लोग डिस्कस करेंगे. सेक्शन बी का भी कंसर्न लेंगे. फ्राइडे कब क्विज होगा, थर्ड क्विज. इतना तक ही था थर्ड क्विज का. आज जितना तक कवर के पढ़ाया, दैट इज द पोर्शन फॉर द third quiz, right? Fourth model next and onwards. Tomorrow fourth model will start. WDM systems. ठीक है. क्या कुछ बोलना चाह रहे हो, बोलो. कुछ बोलना चाहते हो?
सर वही
हाँ बोलो।
पहले से ही क्विज है सर उस दिन, तो फिर दो वही।
लेकिन हम तो पहले 15 दिन पहले हम बता दिए थे, लास्ट वीक में बता दिए थे कि क्विज होगा फ्राइडे में। फ्राइडे
ओके
में
सर।
क्विज होगा, हम पहले, हाँ पहले ही बता दिए थे। ये तो नया नहीं है, आज नहीं डिक्लेयर नहीं कर रहा है, वो पहले से ही बता हुआ
सर
बता दिए।
सर मंडे नहीं हो सकता सर?
मंडे तो हम बता नहीं सकते, क्योंकि क्लास कल आप बताएंगे। सेक्शन बी अगर राजी हो गया तो तुम लोग को देना ही पड़ेगा।
ठीक है सर।
ठीक है। हाँ, क्योंकि पहले से डिक्लेयर है, वो टीचर को से बात करके ही तुम लोग को बता दिए थे।
यस सर, अगर पॉसिबल हो तो मंडे ट्राई कीजिएगा सर, वरना।
पॉसिबल है तो कल देखेंगे, कल पूछेंगे। कल
यस
पूछेंगे,
सर।
अगर राजी है तो मंडे होगा, नहीं तो कल ही फ्राइडे ही होगा। ठीक है।
ओके सर। ओके सर।
हाँ।